Hello, this is a lecture for the Combinatorics class based on the textbook Combinatorics and Graph Theory. This is section 1.1.2, the second part, part B. So this is the second theorem in this book. It says that in a graph, if you have two vertices u and v, and you have a walk from u to v, so remember that a walk is a sequence of vertices, and you are allowed to repeat vertices. So the theorem says that such a walk must contain a path from u to v. And remember that a path means a walk, but with distinct vertices. So here's a proof. So we'll do this by induction on the length of the walk. So let capital W be a UV walk in G. So we want to prove this by induction. If W is of length 1 or 2, then we can check that W must already be a path. So if the walk is of length 1, then this is the only possibility. So here's the U and this is the V. And if it's of length 2, then it must look like this, where you have 3 distinct vertices. So it's not possible to have this situation where first you go from one vertex and then back, because here we're assuming G is simple. So this theorem would be for simple graphs. Okay, so for the induction hypothesis, suppose that this result is true for all walks of length less than k, and now suppose W has length k. So then we can write W in this way, where we have a sequence of k plus 1 vertices, starting at U, ending at V. So let's say in my example here, I have a W, and here my length is k equals 4. And here, so W is just assumed to be a walk, so the vertices are not necessarily distinct. So if the vertices are in fact distinct, then W itself is the desired UV path. If not, let J be the smallest integer such that the vertex Wj is the same as vertex Wr for some r bigger than j. So in my example here, we have the situation where the vertices are not distinct, because here we go to this vertex twice. So in this case, the smallest integer, j, would be 1. And then here wi is the same as w, or w1 is the same as w3. So r in this case is 3. And so let w sub 1 be this slightly shorter walk, where so we walk as normal up to wj, but then basically just remove this extra part and start again from wr plus 1. So in our example, this is my w sub 1. Right, so this walk has length strictly less than k, because we've removed all of the vertices between j plus 1 to r. And so because this walk has length strictly less than k, we can apply the induction hypothesis. So the induction hypothesis implies that W1 contains a UV path, but W1 is already part of, so W1 is a subpath of W. So this means W contains a UV path. And we are done. All right, so here are some more definitions. So we want to introduce 2 different operations on graphs. So one is vertex deletion. So a vertex deletion, if you have a graph and a vertex, so G minus V would denote the same graph as G, but you remove the vertex V, and you also remove all edges incident with V from G. And if S is a set of vertices, we say that G minus S would be the graph G, but we remove every vertex in S, and then all of the edges incident to the vertices in S. So in this example, if this is my G, let's say I remove the vertex D. So that means I remove that, but I also have to remove all of the edges adjacent to D. And that is why I get this picture. And if I remove the vertices F and G, then I remove the edges associated to them, and I get this picture. And then another operation is called edge deletion. So G minus E, if E is an edge of G, is the same graph, but you remove the edge E, but its end vertices would stay. And again, if you have a set of edges, T, then G minus T is the same graph, but you delete every edge of T from G, but their end vertices would stay. So in this first example, if we remove the edge C and D from the picture, we get the same graph minus this edge. And if we remove these two edges, so we remove EG and we remove FG, this vertex would still stay, and E and F would stay, and we get this picture. And we say that a graph is connected if every pair of vertices can be joined by a path. So this graph is connected, but this is not connected, and this is not connected. So each maximal connected piece of a graph is called a connected component. So G1 has just one connected component because the graph is connected. G2 has 3 connected components, so 1, 2, 3. And then G3 has 2. So this is one, and this is the other one. And here are some of the exercises that I ask you to attempt. So for the first exercise, the question is, if you're given a graph of order n, what is the maximum number of edges in G? So for example, if n is 5, then you have 5 vertices, like in this picture. So in order to have the maximum number of edges, you basically have to just connect all of the vertices. So you can count that for n equals 5. So you should generalize that for a general n. The second question is asking that, suppose that you have a simple graph. So all of these graphs will be simple. And then it has 2 vertices, at least. Then the degree sequence has at least 1 pair of repeated entries. So this is similar to some of the problems you did at the beginning of the semester using pigeonhole principle. So try doing this by contradiction. So let n be 2 or larger, and you can just suppose that the degree sequence has no repeated entries, and then see what are the possible degree sequence where all entries are unique, and then you should get a contradiction. So the next question would be 3 for part A. So how many different paths have this C as an n vertex? So let's say the ending vertex. So let's count this by length. So for the length 0, if you want to end at C, then you would just have the path that's just C. So there's only one. And then for paths of length 1, so basically you can start from any of these other vertices and end at C. So this should be the number of vertices except for C, so that should be 4. And then for length 2, you can look at the paths of length 1 and just think, what are the other option. So like, let's say I have this path, which is of length 1. So because for a path, you have to have unique vertices. The only other options for your starting point would be E, A, or B. So that's why this would be 4 times 3. So repeat that logic to finish this. And then for how many different paths avoid vertex C together? So here basically you can consider the edge that you would get by vertex deletion, so G minus C. So that would basically remove all of the edges adjacent to C, so you would get this picture. So from here, you can compute all of the possible paths. So the next question is, what is the maximum length of a circuit in this graph? So remember, a circuit would be a closed trail. So it has distinct edges. So try finding a circuit that's as long as possible. So one possible circuit would be this. So this has 1, 2, 3, 4, 5, 6 edges. But I claim that the number is bigger than 6. And then for this question, again, you can look at this picture, because this is basically the graph with vertex deletion at C.